Hey guys, I'm back with episode 19 of Scientific Drinking, and today, just like most of you, I'm probably going a little bit crazy, cramped up inside. You know, I'm so crazy, I don't even need my notes. That's a lie. They're right here. That was last week's notes. So today we're talking about why we need rockets. People have been asking me to get back to some more space-y stuff, and considering that's what I'm best at, I happily oblige. So today we're gonna be looking at 5 different methods of accelerating things to orbital speeds without using rockets, and explain really why these things aren't implemented today and why we still need rockets. So here we go. Welcome to Scientific Drinking. Cheers. So the number one option is guns, big guns. And we're not talking about the guns people are panic buying right now along with their toilet paper. Yeah, can I get a large order of toilet paper, 2 AKs, and a Diet Glock, please? No, we're talking about some really big guns. We're talking about 16-inch guns. For the record, they use 16-inch guns for battleships that went from World War II all the way into the Desert Storm era, right before the last battleship was decommissioned. But these 16-inchers are vastly exaggerated. They would not fit on top of a battleship. No, these are monsters. There were 3 tests, each got incrementally larger, and they're part of a joint project between the US and Canada to try and develop a launch system that would fire something into space in the 60s. And this was called the HARP project, or the High Altitude Research Project. And it resulted in some of the biggest guns ever made that fired at the highest velocities we've seen so far, a whopping 2.1 kilometers a second velocity. Now, for the record, orbital speed is about 11 kilometers a second, so a far cry from what we actually need. And that's kind of part of the problem with these really big guns. Now, for the record, this HARP gun was 119 feet long, which equates to about 36.3 meters long. Absolutely massive. And like I said, it had a 16-inch barrel. And when it fired, it was loud, really loud. Now, the idea of using a big-ass gun to go into orbit isn't really new, right? Sir Isaac Newton hypothesized that if you could fire a cannonball faster and faster and faster, eventually it would go further and further until it was in orbit around the Earth, of course, if you ignored air. And then, of course, in Jules Verne's 1865 novel, he hypothesized about using a really big gun to go from the Earth to the moon. Much later, you know, in the early movies, The Trip to the Moon, they used a bullet, a manned bullet, if you believe it, when they put people into a manned bullet and fired it to the moon. Now, the biggest problem is you can only get so much velocity out of chemical energy. Granted, you can get a lot in certain situations. You know, chemical energy is what fuels supernovas, well, nuclear energy, right? And those spray particles at damn near the speed of light. But that takes a tremendous amount of energy and something that we can't really reproduce on Earth. So there are limitations to chemical energy, and in fact, it's those limitations that we're facing when dealing with rockets right now. There's only a certain amount of speed you can get from particles caused by an explosion, and that's called ISP. That's what the efficiency of rocket engines are. How efficiently can you combine hydrogen and oxygen to create water, which is the fuel for NASA's SLS space system, for example, and what was used for the Saturn V rocket. Now, it was selected because it has a very high ISP, or specific impulse. But even with that, you're talking about 400 seconds. Not nearly enough to accelerate something to the speed of light, and just enough to get us into orbit. The same rule applies to projectiles. The more you can dump a certain amount of energy into a cannon, but the barrel length is going to become longer and longer and heavier. And really, you're running into a problem with materials, you're running into a problem with chemical energy. And of course, that's not even bringing into the question manned space systems. I mean, the acceleration would have absolutely killed you if the heat didn't. So that brings us to number 2. Mass drivers are kind of like projectile weapons. In fact, they are projectile weapons. They're rail guns. You charge a couple of rails, and the movement of charge from one side to another accelerates your payload until it exits the other end. You may have seen a few videos where the Navy has tested a new prototype railgun that they're thinking about mounting onto ships. That being said, mass drivers do hold a lot of promise, especially if you manage to get the end of that mass driver outside of the Earth's atmosphere, which would require some kind of megastructure. Even so, if we put something like a Falcon Heavy onto a mass driver and accelerated it, every little bit of acceleration you had on the mass driver would be acceleration you didn't have to use in chemical energy. So even a small boost from a mass driver, relatively small, something like 300 meters per second, would be a dramatic reduction in the amount of fuel needed for your payload. The big downside of mass drivers is, of course, the tremendous amount of capital investment you need to make to just build one of these structures. Even a small mass driver, something about 2 kilometers long, would be billions of dollars to construct. But the benefit to something like mass drivers is that it has no greenhouse impact, especially if you're doing something like nuclear or fusion energy. Then you don't have to worry about any carbon footprint at all. Well, assuming you have a really long mass driver here on the surface and you have the infrastructure in place and you can power it with it, dump enough power into the system, and you can accelerate your payload to about 11 meters per second. That is hypersonic speeds on the surface. You're going well past the speed of sound. Even assuming that the sonic boom didn't rattle your payload off the tracks, the heating itself will just disintegrate your payload unless you have a tremendous ablative layer, or you've answered this question with some other kind of sci-fi material. I recently got reminded of the idea of mass drivers from a game called Soma, which was on sale in Steam, so if you get a chance to check it out, I highly recommend it. And a similar concept actually existed where you had an underwater mass driver that led to the surface of the ocean where you accelerated your payloads to orbital speed. If you're shooting your payload directly up, you're of course spending less time in the densest part of the atmosphere, and maybe it will work. The Quick Launcher Space Gun was one of these concepts that existed in 2005, proposing a deep sea space launch system that launched to the surface of the ocean to get you into orbit. Now that brings us to the space fountain. Basically the idea is that you shoot your fuel up into orbit, into your rotating electromagnetically charged loop, which spins the fuels around, ignites it, and shoots it back down towards the Earth. The higher altitude this loop is, the less fuel you need to shoot up to keep it in orbit. Of course, you get to the point where you're in geostationary orbit, and you don't need fuel to keep yourself up because you're completing an orbit around the Earth at the same time as it takes the Earth to spin beneath you, so you're not moving, right? So the amount of fuel required for station keeping is relatively minimal. That being said, you can have something in low Earth orbit as one of these rings that you're constantly shooting fuel up to using a mass driver placed on the surface, and it's igniting that fuel, sending it back down, and you have this constantly rotating ring in space. Now, the advantage of this system is that you can deliver cargo and payloads using this mass driver directly above you without needing that same orbital velocity, and you can supply a kind of low Earth orbit infrastructure. One of the problems with the space fountain, one of many problems, is that it's dependent on this constant fuel source going up. So if that supply chain is interrupted, guess what's coming down on top of you? Problem number two, of course, is the fact that this is requiring a tremendous amount of precision. So the amount of fine control required to keep something in orbit like this is fantastic. In the fundamental definition of the word. Now, if you thought the space fountain was kind of fantastic, you should consider the launch loop. Now, the idea behind the launch loop is you have something that's several thousand kilometers long, notionally about 2,000 kilometers, and you have a loop of material that's constantly spinning. Now, if you've ever seen someone take a bowl full of chain link or some kind of rope and you pull out the end of the rope and throw it down, it's going to continuously feed out until that bowl is empty. Now, this is called the chain fountain or mold effect. Now, the launch loop kind of uses this mold effect and exploits it to the benefit of launch systems notionally. And where you have this link, this tether, that's going back and forth between 2 points in a big loop. And it's going faster than the rotational speed of the Earth, causing it to actually hover above the surface, just from the momentum alone. Now, if you were to accelerate a payload and attach to this tether, you would be carried up into this really high orbit. Now, keep in mind, this thing's 2,000 kilometers long, so where it's rising above the surface of the Earth is at a reasonably high altitude. It doesn't require a tremendous amount of infrastructure, relatively speaking. I mean, relative when talking about other megastructures. You will be able to deliver payloads into orbit at pretty much no chemical cost, right? This entire launch loop can be fed by nuclear or fusion power plants or some kind of green energy that doesn't really have a carbon footprint. So you can keep this going very affordably, or at least that's the idea. Of course, the cost of implementing something like this is tremendous. We don't fundamentally need to develop any new technologies. All the technology we need to build this should be here. However, it is a tremendous feat of engineering. Think of something spanning the entire distance between California and Texas, or Spain to Ukraine. Now, the next idea, in similar terms, does not require any fundamental new technology to be developed. And I'm not going to talk too much about this, and the reason is because Kurzgesagt already did a great video on that, and that's in the link below. And that's the skyhook. Which the idea behind the skyhook is simply a rotating platform in orbit which sweeps one arm into the atmosphere, picking up a payload and flinging it into space. However, if the same number of ships that was returning from orbit were going into orbit, the net amount of energy would be conserved. The biggest drain on energy would be atmospheric drag. Every time one of these big arms would sweep into the atmosphere, it would slow down your skyhook and it would need to be boosted back into orbit. That being said, like I said in the beginning, no fundamental change in technology or launch resources would need to be changed in order to implement this technology. It would definitely be considered another megastructure. And speaking of megastructures, we have the space elevator. Now, there's been a lot of talk of space elevators in the sci-fi community. This appeared in Ben Bova's book, Moonrise, and other pop culture references. So it shouldn't be a surprise that the space elevator makes this list. Now, the concept of the space elevator is basically if you had an asteroid and placed that in geostationary orbit and then connected a tether between the asteroid and the surface of the Earth, you could deliver payloads back and forth to geostationary orbit as much as you wanted. It could be run off of renewable energy, and you could really do this for a very, very long time. The problem with the space elevator, in contrast to something like the Skyhook or the launch loop, is that you need a fundamental shift in materials research. And this is what's going on in hypersonics right now. We're pushing the boundaries of hypersonics, and everything that they need with hypersonics is really comes down to a question of materials. In the case of the space elevator, it's not a question of temperature so much as tensile strength. The only thing that we know of that can handle the amount of tensile strength required to maintain the position of an asteroid in orbit, or just to handle the compression strength of being stacked so high, is buckyball cables or carbon nanotubes. But the bottleneck with this, of course, is that we can't produce these kinds of materials very easily. It's very expensive and very time-consuming to produce small segments of carbon nanotubes or buckyball cables. And the question of producing tens of thousands of kilometers of it, pretty much, well, out of the question. And if you're talking about implementing some of these ideas on planets other than Earth, such as the moon, a space elevator doesn't seem too ridiculous. A little bit of station keeping would be needed because the moon is tidally locked with the Earth, so you'd need something at the L1 point connected to the surface of the moon, which requires a lot less in terms of tensile strength than a geostationary object in Earth orbit, because considering that the moon's gravity is so much lower than the Earth's. Another idea that would be perfectly suited to the moon is something like a mass driver. So even something like a chemical gun might work on the surface of the moon. Remember, I said that the HARP gun had a final velocity of about 2.1 kilometers per second. Now, the escape velocity of the moon is about 2.4 kilometers per second. So it wouldn't be too much of a stretch, assuming you had the lift capacity to deliver something as heavy as the HARP gun to the moon, to install that to deliver payloads, well, unmanned payloads. So with all these ideas in the back of our mind now, we can understand why we're still using rockets. A lot of these other options for delivering payloads into orbit are pretty expensive and require a massive amount of investment, something even the United States government probably wouldn't want to invest in. So thanks for watching this episode of Scientific Drinking. Next week is episode 20, and notionally I had planned an interview. I'm not sure how I'm gonna do that, assuming COVID-19 is pretty much taking over our lives. So stick around, thanks for watching, and see you next time. Cheers.